Welcome to Chapter 5, Section 5, Derivatives of Higher Order. In the previous episodes, we defined the derivative of a real function, proved the mean value theorems, saw that derivatives have the intermediate value property, and put everything to work in Lopital's rule. In this short episode, we take a simple but far-reaching step. The derivative of a function is itself a function, so nothing stops us from differentiating it again and again and again. This gives the second derivative, the third derivative, and in general, the derivative of order n. Getting the definition and its fine print exactly right is the goal of this section, and it is the doorway to Taylor's theorem, which is coming in the next episode. Let's dive in. Here is the plan for this episode. We start with motivation. Why would we want to differentiate more than once, and what do repeated derivatives measure? We then state definition 5.14, which introduces the second derivative and the whole tower of higher-order derivatives, and we fix the notation. Two short examples show the two possible behaviors. A polynomial, where derivatives of every order exist, and a function whose tower of derivatives stops after one step. After that, we look carefully at the fine print of the definition. What exactly must be true near a point for the derivative of order n to exist there? Finally, we summarize and preview Taylor's theorem. Let's set the stage. The derivative f prime, which we constructed in section 1 of this chapter, answers a single question. At each point, how fast is the function f changing? Geometrically, it is the slope of the tangent line to the graph. But this answer immediately suggests a follow-up question. Here is the key observation. The derivative f prime is not just a number at one point. It is a function in its own right, defined on the interval wherever it exists. And whenever we have a function, we can ask our favorite question about it. How fast does it change? Applying the derivative to f prime gives a new function, written f double prime, which measures how the rate of change is itself changing. On a graph, this is the bending of the curve, whether the slope is increasing or decreasing as we move along. And of course, there is no reason to stop at 2, differentiating again and again, as long as the derivatives keep existing, produces the third derivative, the fourth derivative, and in general, the derivative of order n. These higher-order derivatives are far more than a curiosity. They are exactly the raw material of Taylor's theorem, which we will prove in the next episode, and which approximates a function by a polynomial built from the values of its higher derivatives at a single point. First, let's look at a familiar physical example. Higher derivatives are already familiar from physics. Suppose s of t gives the position of a particle at time t. Each amber arrow in the diagram is labeled d by dt, meaning differentiate with respect to time. Following the first arrow produces the velocity, how fast the position changes. Following the second arrow produces the acceleration, how fast the velocity changes. The blue box is the position, the green box the velocity, and the red box the acceleration. Newton's second law says that force is mass times acceleration, so the second derivative sits at the very heart of mechanics. Even the third derivative has a name in engineering. It is called the jerk, the rate of change of acceleration. With this picture in mind, let's give the formal definition. Here is definition 5.14 in 2 installments. Suppose first that f has a derivative f prime, not merely at one point, but on a whole interval. If this new function f prime is itself differentiable, its derivative is written f double prime, and we call it the second derivative of f. Notice the two separate requirements packed into this sentence. F prime must exist on an interval so that it makes sense to differentiate it, and then f prime must actually be differentiable. We will return to this fine print shortly. Now, let's continue the process. Continuing in the same manner, we obtain a whole chain of functions, f, then f prime, then f double prime, then the third derivative, and so on up to the derivative of order n. Each function in the chain is, by definition, the derivative of the one before it. From the third derivative onward, we abandon the primes, which would become unreadable, and instead write the order as a parenthesized superscript. The function at the top of the chain is called the derivative of order n of Vf. Let's picture this chain as a tower. The picture on the slide shows the tower of derivatives. We start on the left with f itself in blue, and every amber arrow means differentiate once. One arrow takes us to f prime, another to f double prime, then to the third derivative, and after finitely many steps, we reach the derivative of order n, highlighted in red on the right. Two remarks about this tower. First, it is built strictly floor by floor. Each stage must exist before the next one can even be defined, since each function in the chain is the derivative of the preceding one. Second, there is no guarantee the tower goes on forever. For some functions, it does. For others, it stops after finitely many steps. Let's see one example of each kind. First, an example where the tower never stops. Take f of x equal to x cubed. Differentiating once gives 3x squared. Differentiating again gives 6x. A third time gives the constant 6, and a fourth time gives 0. From then on, every further derivative is the zero function, and the zero function is perfectly differentiable, so the tower continues forever. As the gray remark notes, the same happens for any polynomial. Derivatives of all orders exist everywhere, and beyond the degree of the polynomial, they are all identically zero. So polynomials are as smooth as a function can possibly be. But not every function is so accommodating. Now an example where the tower stops after one step. Define f of x to be x times the absolute value of x, that is, x squared for positive x, and minus x squared for negative x. The left picture shows its graph in amber, a smooth-looking S-shaped curve through the origin. This function is differentiable everywhere, and its derivative is 2 times the absolute value of x. But look at the right picture. In red, the graph of f prime is a V with a sharp corner at the origin. A corner is exactly where differentiability fails, so the second derivative of f does not exist at 0, although it exists at every other point. The tower for this function has just 2 complete floors. This example shows that the existence of higher derivatives is a real restriction, which brings us to the fine print of definition 5.14. Here is the fine print, straight from the book. Suppose we want the derivative of order n to exist at a particular point x. By definition, it is the derivative, taken at x, of the previous function in the tower, the derivative of order Cn minus 1. But a derivative at x is a limit of difference quotients, and to form those quotients, we need the previous function to be defined at all points t near x, not just at x itself. So the derivative of order nn minus 1 must exist in a whole neighborhood of x. If x is an endpoint of the interval on which f is defined, a one-sided neighborhood is enough, and there is a second requirement. The second requirement is the obvious one. Once the derivative of order n minus 1 exists near x, it must actually be differentiable at x. The displayed formula spells this out. The derivative of order n at x is the limit, as t tends to sin x, of the difference quotient built from the derivative of order n minus 1. This is nothing more than definition 5.1, the definition of the derivative from the start of this chapter applied to the function one floor down. So both ingredients matter: existence of the previous derivative on a neighborhood, and differentiability of that previous derivative at the point itself. But notice that the first requirement quietly reaches even further down the tower. Watch how the requirement propagates. The top number line shows the neighborhood of x, drawn in blue, where the derivative of order n minus 1 must exist, with the point x marked in red. But at each point of that blue interval, the derivative of order n minus 1 is itself defined as a derivative. So the function one floor below, of order n minus 2, must be differentiable at every point of that interval. That is the green line on the bottom, with the same point x marked in red, and the amber arrow labeled forces records this implication. The same reasoning repeats all the way down the tower, as the dots suggest. Each lower derivative must be differentiable, hence also continuous, on the whole neighborhood. So a single number, the derivative of order n at one point, silently presupposes good behavior of the entire tower on a neighborhood of that point. With the definition fully understood, let's summarize. Let's review. This section made one definition, definition 5.14. The derivative of a function is itself a function, so we may differentiate repeatedly, obtaining the tower f prime, f double prime, the third derivative, and so on, up to the derivative of order n. Each function in the tower is by definition the derivative of the one before it, and from order 3 onward, we write the order as a parenthesized superscript rather than piling up primes. Next, let's recall the fine print that comes with this definition. Second, the fine print. The derivative of order n at a point x is not a purely pointwise notion. It requires the derivative of order n minus 1 to exist on a whole neighborhood of x and to be differentiable at x, and this requirement cascades down. Every lower floor of the tower must be differentiable on that neighborhood. Keep this in mind whenever a theorem assumes the existence of a higher order derivative. It is quietly assuming a lot of regularity below it. Finally, let's remember the two examples. The function x times the absolute value of x is differentiable everywhere, yet its second derivative fails to exist at 0. The tower can stop. Polynomials at the other extreme have derivatives of every order at every point. In the next episode, this machinery pays off immediately. Taylor's theorem, theorem 5.15, approximates a function by a polynomial whose coefficients are built from the values of f and its higher derivatives at a single point, with the mean value theorem controlling the error. It is one of the most useful results in all of analysis. See you there.